This is a lesson on heat and the heat and thermodynamics unit. I wanted to take a moment and describe heat conceptually to you. If you do not have a good understanding of heat, you will find the material in the upcoming units problematic and have a hard time understanding at a foundational level what's going on. So understanding what heat is a very important factor of mastery of this material. By definition, heat is the flow of thermal energy. Heat is thus a process quantity, and you've seen a process quantity before. This is much like work is a process quantity. Remember, work cannot be embodied by any object. It is the transfer of energy from one thing to another, and that's why we call it a process quantity. We've seen internal energy. And internal energy can not only be just the thermal or kinetic energies of molecules in the system, but we could also see some incoherent chemical or electrical energy. And you would see this in chemistry with Gibbs free energy and enthalpy. Thermal energy is a form of internal energy U. So you're seeing different terms here. There's Q and there's U. A simple model of this process, I'm going to take what you know about mechanical energy, and I put this over here. Some sort of initial mechanical energy, whether it's kinetic or some sort of gravitational potential energy, plus some work. So we have an initial energy state. We add or subtract energy to the system, and we get some sort of final mechanical energy, some kinetic or potential energy. We can think of that with heat. If we have some sort of internal energy state, we could add or subtract heat and have a final internal energy state. While I'm here, I'm going to remind you that heat is an energy, and our units of energy in SI are going to be joules. So if you have any questions about units of heat, it will always be joules. Notice that has to be true in order to use it in energy conservation of energy equations. We may also see calories or kilocalories, which is the big C calories. And there will be conversions for that I will remind you of as we move more into the material. Let's look at this term, thermal energy, a little bit more in detail. Thermal energy is the measure of incoherent motion. Again, and we saw this in the last lesson, these molecules are bouncing around wherever. They're not doing anything coherently at a molecular level necessarily. By coherent motion, I mean all of the molecules are moving in some one direction that would result in translation of the entire object or rotation of the entire object. But for now, we're just looking at the molecules within that substance, and there's nothing coherent going on. They're just bouncing around everywhere. And we saw that the average speed can be related to the object's temperature with kinetic theory. The hotter the object, the faster its molecules are moving within. And this is true for translation, rotation, and vibration. Remember, I introduced the simplest case where we have one molecule just translating, but they could also rotate or vibrate if you were in a liquid or a solid. Again, absolute zero must mean no motion. If there's a zero on this side, there's no velocity. You will see the term thermal equilibrium, and by that we mean that two systems have a same temperature. So two objects in contact with one another, two bodies in contact with one another, means not that they aren't exchanging energy, but that this energy is freely flowing between them at some constant internal energy state that we can measure with temperature. And this is what is meant by the idea of heat death. If you've heard of the theory of the heat death of the universe, when there's no more, it makes it sound like there's no more heat in the universe, but what it means is that all of the energy in the universe has become uniformly distributed across it so that all molecules are on average moving at the same rate. So that's the idea of thermal energy. So we're getting several terms going on here that are very specific and scientifically defined that you will need to master. So let's take a little bit deeper look between temperature, internal energy, and heat. Temperature is intrinsic and it's independent of the size of an object. If you have an object this big or an object this big and you measure the temperature and they have the same temperature, it's intrinsic. They have different masses, but the temperature is the same. It does not matter how much of an object is there. The internal energy U is extrinsic, meaning that it's proportional to the size of the object. And you've seen this before. mgh. This is an intrinsic potential energy. It depends on how much mass is there. If you have a more massive object, you have more energy. The same with internal energy. If you have a larger mass, it has more thermal energy in it. The more mass an object has, the more energy it can contain. And this is a term that can be used in conservation of energy equations. So you saw that in this prior slide. I can use this in energy conservation. Heat can also be used in conservation of energy equations, but it is the transfer of energy. And we see that in the equation I had in the previous slide. All of this adds up to the beginning of the study of thermodynamics. Thermodynamics for me are the rules for energy transfer. We see that there is energy and we know how to relate energy to measurable quantities, but thermodynamics formalizes theory further in saying that energy must flow one way. It cannot randomly flow whichever way it wants. There's rules for energy flow. Internal random energy naturally flows from hot to cold. This is the first law of thermodynamics, and it's very intuitive for you to know that it flows from hot to cold, from high temperature to low temperature. Understanding how energy flows spontaneously, what is the natural course of events, including flow of energy in systems or random motion and how chemical energies interact, are the principles for driving myriad phenomena, and that's why it is fundamental in the general introductory study of physics. Note with all of this stuff that energy is still all accounted for. I keep talking about an initial energy state. There's some add or loss of energy with work or heat, and then that results in some final energy state. Much like your bank account, you have an initial value, you add and subtract some, and you have a final value. Heat goes in here in the add or loss term, and it flows from hotter object to the colder object, and we are going to look at heat transfer models of how this heat transfers in the next lesson. There are various consequences of heat transfer. It causes a rise or loss, depending on which way it flowed, in the internal energy of an object. What if Q is negative? If Q is negative, that means it flowed from the object to another system or object, and that would give it a negative value, as opposed to if it flowed into the object, that's a positive value and it's taking on heat. And we will look at the importance of this as we move through the lessons. This manifests in many measurable ways, which I'm excited to study. We'll get into study each one of the effects. There's some sort of change in temperature. That may be one of your more intuitive notions about this material is when heat flows, there's going to be a change in temperature. There's also a change in size, just like in thermometers. There's a change in structure, physical structure. So you may melt ice, and so it takes heat to melt ice, and there's a change in physical structure. The chemical properties may change, or the chemical composition may change. When you add enough heat to a system, you can get it to separate.